Jai Hind, myself Pushkal Kumar Shukla, Assistant Professor at Ajay Kumar Garg Engineering College in Computer Science Department. Today I will teach you a theory of automata and formal language. This subject is important for the AKTU BTech 4th semester students. Now we will cover a finite automata. Why finite automata is important? The objective of this topic is to make the students able to understand the requirement of the finite automata. Very important, understand the requirement of the finite automata, implement finite automata, and realize the expressive power of epsilon NFA, NFA, and DFA, and then minimize the finite automata. The objective of this topic is this. Now come on the introduction to automata. The term automata is a Greek word, which means self-acting. Automata is a Greek word, means self-acting. The plural of automation is automata. And automation is the system that performs some function without human intervention. It takes inputs, provide outputs, process it, then provide outputs without the human intervention. Automata theory is the study of the abstract computational machine and the computational problem that can be solved using these machines. Abstract machines are mathematical model of a real computation. Here we see this is the CPU which is used for the processing. This is input. Input is coming to this processing unit, that is CPU. There is a program memory where instructions are written, and there is a temporary memory where calculations is going to perform, and then output will be shown. We can see this by example. Suppose we have to compute function fx equal to x square plus 3. So this instructions are written in a program memory in terms of like there is another variable y equal to x into x. Then what we will do here, fx equal to y plus 3. So by this way, so this is written in the form of instructions written in this program memory. Suppose we are passing the value of x equal to 5. So this value is passed to this variable x. So 5 into 5, that is 25. This 25 is passed to this variable y, then 25 plus 3, that is 28. So fx equal to 28. So this computation is performed in the temporary memory, and this computation result will be shown in output unit. So by this way, automata will perform this function, computation of this function. Now different kinds of automata. So automata are distributed by the temporary memory, distributed by the temporary memory. Finite automata, there is no temporary memory here. This type of this memory is not in a finite automata. There is no storage for the computation. Just like as a calculator, it takes inputs, processes it, and provides outputs. Then push down automata, there is a temporary memory that is known as the stack. Stack is basically used for push and pop operation. So stack is there. Then next, Turing machine, random access memory is there, where Turing machine can move left, right, anywhere it can move. So this is the powerful machine. This is the powerful machine in automata theory. So if we're talking about the power of the automata, so finite automata is less powerful than the push down automata, then less than the Turing machine. So Turing machine is the most powerful machine of automata. So the finite automata, that is no temporary memory is there. Finite automata, it takes inputs and then provide outputs. Like example, vending machine, it takes inputs and provide outputs and having very small computing power than the PDA, push down automata, as well as the Turing machine. Next, push down automata. Push down automata example is a compiler which is used in the programming languages. Compilers are the softwares, system softwares which takes input as a high level language, it converts into the low level language. So, compiler is a very important for programming languages like C++ compiler, like Turbo C, Boland C++ compilers, Turbo C++ compilers. So, this type of compilers is an example of push down automata in which it takes inputs, then provide outputs, and there is a storage that is known as a stack where push and pop operation is performed. And this type of problem, suppose a k power n, b k power n, this type of language is performed by this context free languages and context, and the grammar which are associated with this language is context free grammars, and this type of language is associated by the push down automata. Then Turing machine, there is a temporary memory that is known as the random access memory. This memory, the header can move either left or right, both way it can move. So, that is why it is so powerful and having a highest computing power. Just for example, any algorithm. Then power of automata, that is finite automata, is less powerful than the power push down automata is less than the Turing machine. So, this is the less power and this is the more power, so more computational power. Then introduction to automata, basic concept. This is a finite control. In which different states are there. Suppose there is a different states Q0, Q1, Q2, Qn. Suppose n states are there. Initially the control is at the left hand cell, and this is an input tape. This is a magnetic tape where input alphabet that is represented by the sigma, input alphabets are written here, and this is divided into the different cells, square cells, and each cells having capable of like storing one alphabets, and this is the reading head, which are aligned to the leftmost position. When automation initially will be the Q0 in initial state, and the reading head will be at the leftmost position, and if it scans the input, suppose A, B, C, these are the D, E, F, G, these are the symbols which are used in the input tape. So, reading head will be at the initial position and the Q0 state will be at the initial state. So, what this finite control machine will do, this finite control. So, initially it will be Q0 and reading head will be at the leftmost position. So, scanning after A, it reaches to the Q1 state. So, this way it performed actually initially. This is a Q0 state. So, initial state Q0, this is marked by simple arrow, and then if reads inputs A, reading head will scan input A, then suppose it will reach to the state Q1. So, it is represented in a finite automata like this. Again, if it suppose it will read the input B and next state will be Q1, so it will be represented by this. So, by this way the movement is possible in a finite automata. So, every automation consists of some essential features as in real computers. It has a mechanism for reading input tape. This is an input tape. We are reading input alphabets are this is mechanism for reading inputs, and input tape, this is also known as the input tape. The automation can produce output of the sum form, and if the automata is a binary, accept or reject, then it is known as the acceptor. If automata sequence in response to an input sequence, then it is known as the transducer, and the automation may have a temporary storage. And the most important feature of the automation is a control unit. This is control unit. So, control unit initially at a Q0 state, and after reading input from the input tape, it moves to the next state. Application of automata. So automata theory play an important role when we are checking the software for designing and checking the behavior of the digital circuit. This is the application area of the automata theory to checking the designing and checking the behavior of the digital circuit. Second, the important use is the lexical analyzer of a compiler. This is the important phase of the compiler, lexical analysis phase, to where this automata is used. What play there? Actually, the input given is breakdown into the logical units, that is known as input text breakdown into the logical units, that such as identifiers, keywords, punctuations. So compiler break it for the lexical analysis phase. And then next use we can see a software for scanning large body of text, such as collection of web pages, to find occurrences of the words, to find the phrases of the other patterns, etc. And automata theory is also most useful concept of software for natural language processing. So these are the application areas of the automata where it is used. Common term used in automata. First, the alphabet. An alphabet is a finite, non-empty set of symbols. Alphabet is a finite, non-empty set of symbols, and it is represented by sigma. This is a sigma, this is a Greek symbol. For example, sigma equal to 0, 1. So 0, 1, 2 symbols are there, 0 and 1. So it is known as the binary alphabet. Suppose sigma equal to 0, 1, 2, 3 up to 9. So this is a decimal alphabet from 0 to 9, decimal alphabets. And sigma equal to A, B, C up to Z. This is known as the lowercase alphabet. Next, we see example sigma equal to capital A, capital B, capital C up to capital Z. So this is a uppercase alphabet, and so on. So this is what alphabet is. Alphabet is a finite, a non-empty set of symbols. Then strings, your words. String, your word is a finite sequence of symbols over sigma. Finite sequence of symbols over sigma. Just for example, suppose sigma equal to 0, 1. So if we write a string w equal to 0, 1, 0, 1, 0, 1. So this is a string. Your words over an alphabet. Alphabet sigma equal to 0, 1 over this. So W, suppose another example, sigma equal to, this is a input alphabet A, B, C. So we can say W equal to A, B, C, A, B is a string over an alphabet A, B, C. So we can say a string, a word is a finite sequence of symbols over that input alphabet. Next, length of a string. So length of a string, basically we are here power of sigma we are talking here. So for example, if sigma equal to AB, two symbols are there, then we can say a power of this equal to power of it means lambda ya epsilon, that is empty string, that is called epsilon. It means ki empty string. This sigma 1 equal to A and B. Sigma 2, if we are going to calculate, so what we do here, A and B and A and B. So what possibilities are there? AA, AB, BA and BB. Again, if we are going to calculate sigma 3, so what we will do here, sigma square into sigma. So this will be A, AB, BA, BB and again AB. So what type of string is generated? AAA, like this, AAB and so on. So total 4 into 2, that is 8 strings is going to generate. So by this way we calculate a power of sigma. Again there is a term associated, very important, that is used in automata, that is sigma star. Sigma star is a epsilon. Sigma star is epsilon. Sigma star is basically sigma 0 union sigma 1 union sigma 2 and so on, and sigma plus, that is clean closure, is equal to excluding this sigma union sigma square union sigma 3 up to this, up to n. Sigma star equal to यानी कि स्टार ऑपरेशन, स्टार क्लोजर and clean closure and star closure. Next, reverse of a string. So reverse of a string, W is represented by W ka power R. Suppose there is a string W equal to X, Y, Z. So WR is just flipping. So Z, Y, X. Substring of a string, if W, X, Y, Z, then its substrings are, suppose W equal to X, Y, Z. So substrings are epsilon, then X, then Y, then Z, like XY, YZ, ZX and XYZ. These are the substrings. Again, prefix of a string. If W equal to XYZ, then prefix are all the leading symbols of this XYZ. So first leading symbol will be epsilon, then X, then XY, then XYZ. So W equal to XYZ, then it prefix are all the leading symbols of XYZ. And the suffix of a string is, suppose all the trailing symbol of that string. If W equal to XYZ, then its suffixes are first epsilon, then Z, then YZ, then XYZ. Languages, very important. A set of strings over sigma is called a language. For example, if L1 equal to W01, it means that two symbols are there, 0 and 1 and star, any combination of 0 and 1 including epsilon. So W has an equal number of zeros and ones. The equal number of 0 and 1s, so what string is having this language? So equal number of zeros, that is 0 1 1 0 0 0 1 1 0 1 0 1 0 1 1 0 1 0 1 0 1 0 0 1 1 1 0 0 and this so on. So this is language L1. So W has an equal number of 0 and 1 over W equal to 0 1 star. Suppose there is a language L2, W equal to A B star and mod W is less than equal to 3. So what type of a string is generated in this language? That is AB star. So first and length should be mod W equal to less than equal to 3. So the list, the minimum string, the smallest string that is to be accepted by this particular language is epsilon. So epsilon should be there. Then having length 1, that is A B. Yeah, here we can say like 0 1. So it will be 0 1. Yeah, A and this is B. Yeah, AA, AB, BA, BB, like this, AAA, like this, AAB, ABA, ABB, ABBB, and like this. So by this way, and lastly BBB. So we can say this type of string is generated by this language L2, and we say L2 equal to AB star and mod W is less than equal to 3. So this is a language. Language is a set of strings. This is a set of strings over sigma is called a language. Then clean closure. Clean closure represented by a sigma star, and it is a set of strings all possible length, including empty string. So this is represented by sigma star equal to sigma power 0, sigma power 1 union sigma power 2, sigma power 3, and so on. So for example, if sigma equal to AB, then sigma star equal to epsilon AB, AA, AB, BA, BB, AA, all possible length. So clean closure is the set of all strings of all possible length, including epsilon. So epsilon is there. Then positive closure. Positive closure is represented by this positive closure. Is a set of strings of all possible length, excluding empty string. So excluding, so we can write here this equal to this minus this. Yeah, this equal to this union this. Sorry, this. So here we see here epsilon should be not there. Epsilon should be not there. Thank you.